P star Q smaller than 2 is the simplest one. Yes, here there is only powers of n and m depends on P and Q, but there are nothing like square root of P or square root of Q terms. So this is the simplest. Also, when both are big, this is also reasonably simple. And then something is in the middle. Okay, so there are formulas like this based on Chevret inequality. So the first approach would be to generalize Chevret to other random variables. Unfortunately, Chevret is pretty tight, so we cannot hope a very general extension of this inequality. But something could be done, and we noticed with Marta. Okay, so there were some extensions in previous papers, but they were not two-sided. So they were either only works well in some range of parameters. So we noticed that there is actually two-sided bound, like in Chevret inequality. But we need to assume. Okay, so we were able to extend it to the case of variable random variables, but it's a variable with a tail of density doesn't matter so much because both are comparable of order e to the negative t to the r, where r is between 1 and 2. Okay, so when r is 1 is exactly exponential, symmetric exponential. When r is 2 is not exactly Gaussian, because the Gaussian tail is not e to the negative t square, but the density is e to the negative t square, but as I told you, if you don't care about the constant, it is comparable, because the tail of Gaussian is more or less like e to the negative t square. So for 2, r equal 2 is Gaussian, for r equal 1 is exponential, so this interpolates between these two cases, and then there is Chevret type inequality. So notice that these terms are exactly as in Chevret. And this is not surprising because, okay, these random variables have harder tails than Gaussian, so the Gaussian should lower bound this. So then there is this Gaussian term, and then there is also like in Gaussian case linear terms not in now Gaussian but in this variable, and then instead of second norm you have here dual norm to r, where r is this parameter. So for exponential, for example, here will be infinite norm. So previous, for example, estimates on this have here instead of r star 2, and they were only one-sided and worked only in some range of parameters. Okay, so and here there is no dependence on anything. Okay, on r, because r is pretty bounded. Okay, so then you may apply this to our situation. And then the only thing you need to estimate is this LU norm of IID variable. So it's very similar like in Gaussian, but instead of square root of u, you have u1 over r, and you get this thing. Okay. So what should we notice that in the case when p star and q is smaller than 1, it's exactly the same formula as for the Gaussian. And also when p star and q are big, it's not the same formula because there were square root of 2, but pretty nice in this case. Now, okay, and there is something in the middle, not very nice. And the thing simplifies much simplifies in the case of squares because there are then only two regimes and up. Okay, in the first regime it's pretty simple, and then there is this 1 over r part. Okay, and this method could be extended to the situation when coefficients are tensor type. Then I will not present formula because they are pretty longer. Maybe not very awful, but much longer to put on one side. But you can state them. Okay, if tensor type coefficients. Okay, but now. Okay, so this works well when you have Chevret type inequality, but even in the Rademacher case, it's not obvious if there is something like Chevret for Rademachers because it has lighter tails than Gaussian. So I'm not sure if one could get something, but a lot of things were known about Rademacher matrices. So for example, okay, there is a classical paper of Bennett, Goodman and Newman, when they treated these operator norms, okay, more or less, for sub-exponential random variables, in particular Rademachers are in this class, and they get these bounds, so pretty simple bounds, but here there was dependence on P and Q. Yes, so and then the argument was standard, like on the basis of Laplace transform and netting argument. Okay, and then as of now, okay, so this paper is still not published, but it was put on the archive like a few years ago. He noticed that if you have Rademacher's square matrix, then this Bennett-Goodman-Newman bound could be reversed. So here the constants does not depend, in fact, for Rademacher's on P and Q. And by the way, okay, for sub-exponential, this is the result also for sub-exponential, if you allow this dependence. Okay, so this is the result. So if you put n equal to m and then it's clear, it's not hard to notice that this reduces to this because of some trivial estimates. Okay, so not that terrible band, but so the first question is what is going on if n is not equal to m for Rademacher? Is this the same as in Asaf result that you may put here there is no dependence on P and Q in this bound?
On the left hand side there's n equal m or?
Here n equal m, yeah. Here is n equal m. Oh, I'm sorry. I put some copy and cut and paste and okay. The title of the slide is right, but this is okay, I'm sorry. Thank you for being okay. So what is the situation for n not equal to m? So okay. So in this case nothing happens, this is the right bound. So maybe let's look at this case. There was n to the 1 over p star plus n to the 1 over q. Now it's this, but you should multiply this by factors which depends on m and n. And it's like m to the 1 over q. So if q starts to be like log of m, then this disappears. But if q is like 4 or something, then this factor, okay, here is also, okay, if q is like 4 and p star is not too small, because then it will be q star to the 1/4, which is still a constant if p star is small, but if q star is of order m, let's say, and then q is 4, then this matters. Yes, so this is not the case, but in this Bennett-Goodman-Newman estimate, you may just forget about dependence on Q. You should ask. And this was our first result without using this Chevet type bounds, and then the argument was like in maybe previous bounds. So then, okay, you use netting argument, but then after netting argument, you observe that Rademacher has much tighter concentration than Gaussians, and you may gain something on them. Yes, so because they are bounded, so there are some a bit tighter concentration inequalities for Rademachers, and then if you apply them, okay, you get like this, and then you notice that in fact they may be reversed. Okay, so the next question. Okay, so we have this result for Weibel, in some range of Weibel for Rademachers. So is there something much more general? And in fact there is. So what we were able to get is the following condition on the IID coefficients, namely regularity in terms of moments. So if you get like two raw moments, it's comparable to raw moment up to a universal constant. So for example, for Gaussian, raw moment is like square root of rho. So this alpha is basically square root of 2. For exponential, moments are grows linearly, so basically this alpha is like 2. In general, so for example, for Rademachers, the moment are 1, so alpha is 1. But for log concave, also log concave grows in linear way, so alpha is more or less like 2, a constant. But for Weibull, it's like 2 to the 1 over r. So if this parameter is not very close to r, then the inequality to 0, the inequality holds. Okay, if you don't like this moment assumption, you may have the assumption in terms of tails equivalent to this. So equivalent in the sense that these two constants depend on alpha, and if you have such inequality, alpha depends on these two constants. And this is like this, but if you so basically if you instead of this look at the log tail function, so put a log, then this log tail function would be doubled if we multiply t by a constant. Okay, so for the people who prefer thinking, so I think statisticians will prefer to look at tails and moments. Okay. So
C1 is bigger than 1.
Sorry?
C1?
C1 is obviously, because otherwise... yeah, okay. Probably you may show that if C1 is smaller than 1, then the variable should be constant. Okay. C1 and C2 are universal. Okay, and then so the statement is like this. But if you have this assumption, alpha regularity, then we have this formula. So there is some supremum here. So I will show in some examples that it's not very hard to get rid of this supremum. And but what is the gain here? But this is linear. Yes, so like in Shabbat, this is linear in terms of xi, and supremum is outside. Yes, so you need to just to estimate the moments of linear combinations of variables in rows and columns. Okay, and the formula simplifies a lot in the square case. So if n is equal to m, then okay, it's like this. So when q and p star are below 2. This is like standard deviation times this n to this power, like before. And if q and p star are one of these is bigger, it's like 1 over p q minimum q times this moment. And okay, for this random variable, the moments are comparable to the log tail function. So for example, in all these cases, like variable, it may be you may either compute it analytically what is a moment, because it may be expressed in terms of gamma function, but you may also, if you have a tail, use this formula and get immediately, for example, moments of variable are when n inverse is t to the 1 over r, so then this is like rho to the 1 over r. Okay, so there is obviously a version for non-centered variables, but this is kind of trivial, because you may put expectation inside and subtract the expectation. This is centered, so you may apply previous result, and this is constant. So this may be constant. So this is trivial remark. Okay, maybe I will not torture you with exact expressions, but maybe let's look how it works for in the square case for variable. Then, okay, for p star and q small, this is like this, like what it was for Gaussian or Rademachers, and okay, it should be bigger than 2. If p star and or q is bigger than 2, then this tends to be n to this power times minimum p star q and log n to the 1 over r. Okay, there are some formulas for rectangular, but I will not discuss them. So why this alpha regularity comes into picture? Why this is of some help? This is because there are two things for such random variables, and the crucial one is this, which also may be formulated in terms of some concentration equality. That is, if we compute a moment of suprema of linear terms, then we may put this suprema outside, but in the cost of some of expectation. So here the lower bound is trivial, yes, because this is LP norm is always bigger than first moment, and also putting suprema outside decreases the expectation. But what is not trivial, that there is an upper estimate on this form, and this is the crucial in all these calculations. Another is like hinge and type inequality, which basically states that also linear combinations of such random variables have some regularity. Yes, so when they are almost alpha regular, so alpha a bit changes, but not in a controllable way. So these are two main tools, and maybe okay. One more remark. So I gave you a formula for expectation, but from this formula we get also formulas for tails or higher moments because of this comparison of moments I was giving you on the first slide, because this is suprema of this thing, yes, of this linear terms. So we put the first moment and suprema outside, and then compute things like this. So this is just real random variable combination of these things, and there are a lot of inequalities or exact formulas even for this. So this usually is easy to compute. Okay, so maybe I will not give you the lower bound. The lower bound is pretty easy. It still requires this alpha regularity, but it's basically based on clever use of Paley-Zygmunt inequality. But let me just show you two elements of the proof for the upper bound. So because they are depending on the range, they are different. So in this range, when both P star and Q are small, the formula is pretty simple, as you noticed on the first slides, and it's based on the following trivial estimate: that if you want to compute the norm from LP to LQ, you may just compute the spectral norm and factorize it by the norms of identity. So very crude estimate, but in this range it works. So basically, if you use some bond, okay, Seginer type bond, I was having a paper extending somehow Seginer a bit under some assumptions. Then if you apply this, you get this. Okay, so and then notice that here the assumptions are less restrictive than IID. We need only to assume identical variance but first and second moment are compatible. Okay, so let me show you something in the case when P star and Q are big. So in this formula there were forms like Q minimum log M, yes? So why the thing stabilizes after log M? This is because the following thing, that if Q is bigger than log of dimension, then LQ norm is L infinity norm. Exactly. So when Q is big, then instead of computing LQ norm, you compute L infinity norm, that is maximum of independent things. And then also there is another crude estimate, that how to estimate the maximum of independent or dependent random variable. Here it doesn't matter. So when the first moment is smaller than log moment, okay, any piece moment bigger than 1, then this is maximum is smaller than sum, yes, and then if they are IID, yes, okay, or if they are not IID, then you have this maximum, and here there are k terms, and k to the 1 over log k is at least e. So you have this very simple estimate, that E maximum of random variable is smaller than E maximum of L log Q norms of this. And if you apply this to this thing, here you have maximum of M things. So then you will get this thing, but the norm log L log m of this thing. And then, again, apply comparison of weak and strong moment. This is the first moment, plus this supremum, which actually appears in the formula, so with t outside. And this may be estimated pretty easily. Okay, so these are two ideas of the proof, but actually the fun started when Q is bigger than 2 but close to 2. And then the calculations are slightly more delicate. So I'm running out of time, so maybe 2 open questions, which are not, I think, important but not trivial. So first, okay, I provided you two-sided bond with some regularity assumption. In the second result I started with, but the spectral norm is maximum of rows, length of rows plus maximum length of columns. There is no regularity assumption. So the question is, can we get a very general Seginer type result? We don't know. The second much, okay, very hard question probably, is okay, what if we don't have IIT case, but we have structure case? So the coefficients are not tensor, not 1, but just arbitrary. So the case of spectral norm is now pretty well understood, at least in the Gaussian case. But if you go outside of this case, there are lower and upper bounds and some conjectures, but still the difference between lower and upper bounds are at least log to some powers, log of dimension to some powers. And there are 2 results in this direction, one of Gedon, Hilsdijk, Litvak, and Prochno. And so this works, I guess, in the case P star and Q smaller than 2. And then another paper when there was actually conjectures what it could be, at least in the Gaussian case. And we, together with Marta, we verified this conjecture in the case of tensor coefficients. Okay, so thank you, and I'm sorry for being too long, but I started 5 minutes.